What it is that I do now and how I got there. So the title of the talk is called My Road to Silicon Valley, which I didn't really think too much about because it kind of makes it sound like it was some far off mysterious land. We're here, we're right here actually. So anyhow, so I am a circuit designer. I'm a circuit designer at a company called Inphi Corporation, and what we do is we design and sell chips, connectivity chips that allows data centers to communicate with one another and allows communication within a data center. Now, just a little bit about our company. We were founded in 2000 and we went public in 2010. And we are a fabless semiconductor company, which basically means that we don't manufacture the chips. We just design them, we outsource the manufacturing. We're about 450 employees worldwide with 75% in engineering, which makes sense for being a tech company. And we pretty much provide solutions for the optical, networking, and memory markets, and we focus on telecommunication providers and data centers. So on the optical side, what we do is we design linear drivers and amplifiers to allow data centers to communicate with one another. And on the networking side, we design high-speed transceivers that enables communication within a data center. And on the memory side, we design registers and buffers that allows high-speed connectivity between the central processing unit and the memory. So the demand for this high-speed data transmission is pretty much driven by the rise in a bunch of applications such as social media. I mean, who's not on Facebook or Instagram, as well as who doesn't shop at Amazon via e-commerce, as well as the cloud. A lot of folks are now putting their data, their files in the cloud. Okay, so moving forward, I work in the networking interconnect products division, where we provide 100 gigabit per second connectivity chips that are industry leading in performance and power, and also is in line with the roadmap to higher modulation digital signal processing, which in short terms basically means we pack lots of data and ship it at one time. So I was involved in right out of school, I was involved in a 40, 50, 100 gigabit per second PAM4 transceiver. And a transceiver is simply just a device that accepts data and ships out data. So here we are receiving data from the cloud and we spit data back out to the cloud. On the other end, we're shipping data to the network and receiving data from the network. So this basically allows connectivity between the cloud and the network. And I was involved in this transceiver portion, but the whole chip was a massive system-on-chip system that involved two transceivers and a huge digital signal processing engine, which I need another Ph.D. to completely understand. So this is the chip microphotograph, basically the die, how it looks in real life, and the transceiver portion that interfaces with the cloud is on the bottom here. The dimensions are 4.9 millimeters by 6.3 millimeters, and just to size things up, this is roughly 10 times smaller than a penny. Now, the whole scheme is data transmission, and that's what we do, and we do it as fast as possible. And this is how it's done traditionally is you would send a series of signal pulses that can be identified as a 0 or a 1, or a low or a high signal. Now, the diagram that I'm showing here is this plot is essentially the signal itself when displayed and plotted over one cycle, one clock period. So you can see a well-defined low and a well-defined high. Now, this eye diagram allows us to observe the quality of the signal being transmitted. In this case, we're transmitting a signal at 20 gigabits per second. That's roughly a 35 picosecond clock period. Now, a picosecond is 1 second divided by 1 trillion, just to give you an idea of how fast this is going. Okay, so the industry trend now is to go to a new signaling technique, which is what we do, called 4-level pulse amplitude modulation, or PAM4 for short. Now, PAM, what it stands for, basically is, like I said, pulse amplitude modulation, but what it does is it encodes the information in the amplitude of a series of signal pulses. So over here, this amplitude would give us a 0, 0 to 0, 1 to 1, 0 to 1, 1. Essentially, it gives us 4 levels, 0, 1, 2, 3. So So with this signaling scheme, it allows us to transmit twice the data in a single shot. So the way I like to think about it is, so now back in the day when I used to upload some selfies to Facebook, this is how it would be done. But with this, I can upload 2 of them at the same time. So. Okay, so the portion of the actual transceiver that I was involved with was the receive side. Now, as I showed you, we ship out a PAM4 signal, but we have to detect it on the receiver side. We have to detect whether it was a 0, 1, 2, or 3. And one way of doing that is with what we call a analog to digital converter, or an ADC for short. Now, essentially what an analog to digital converter is just a device that approximates a continuous time signal, or an analog signal, and translates it into a discrete time signal, or a digital signal. You can think of it as a bridge between the world around us and the world of computers and modern electronic devices, because essentially everything in the real world, like sound, temperature and pressure, is continuous in nature, but computers only understand zeros and ones and discrete values. So what the analog to digital converter does is it takes in a continuous time signal, samples it, and it spits out digital values that is a representation of an approximation of the input signal. Now, the speed at which you do the conversion and the accuracy of the conversion depends on a parameter we call the ADC resolution, or the number of bit streams that get sent out, and how it represents the value being sampled, as well as how fast you're doing this with the clock period. Now, the fastest and the most simple way of doing this is with what we call a flash analog to digital converter. Now, let's not get intimidated by the structure. It's really simple, so let's just go over it. As you apply a continuous time input signal at the input, which is sampled and tracked on a storage element. Now, when the switch opens up, this sample signal gets presented by this buffer, gets presented to a set of what we call comparators. Now, the input to this comparator is the sampled signal, and on the other end is a reference voltage. Now, these comparators is going to compare the sampled signal with a reference voltage, and is going to spit out either a low if the signal is below the reference voltage, or it'll spit out a high if the signal is above the reference voltage. So these bits coming out will get encoded into a digital word whose length depends on the ADC resolution. So as an example for this 2-bit flash ADC, if the input signal that varies between 0 and 1 volt is being converted by the flash ADC, it will spit out a 00 if the input signal sampled is below 0.25 volts. It'll spit out a 01, or a value of 1, if it's between 0.25 and 0.5 volts, and it'll spit out a 10 if it's within the 0.5 and 0.75 volts, and on the extreme, it'll spit out a 111 or a 3 if it's above 0.75 volts. Now, this architecture has the advantage of it's the fastest and most simple way of doing a data conversion, and it's the only architecture that allows you to do it in one shot, one cycle. However, as you can see, for higher resolution, for here we're representing a continuous time signal with only 4 values. However, for higher resolutions, you're going to need a lot more comparators, and this is exponentially dependent on the desired resolution. So for only a 2-bit ADC, we only needed 2 squared minus 1, 3 comparators. But if you think about for 8, say a resolution of 8, where this analog signal could take 1 out of 256 values, you're going to need 2 to the 8 minus 1, or 255 comparators. Now this could pose a problem for high accuracy, even though it's the best for high speed. So we won't get into too much details, but let's just want to get a feel for what is limiting the high-speed operation for this thing at high resolutions. Now, this buffer has to present the sampled signal to the comparators quickly if you want to operate your data converter fast. And this buffer could be modeled as just a simple GM stage, and unity gain feedback. Now all this does is that it forces, the feedback forces this voltage here to be equal to this voltage and present it to the output. So it's just a unity gain feedback. Now this storage element, this load capacitor, we can just picture it as a quantifies the load that's presented by these comparators here. So the more comparators you have, the larger this capacitance is going to be. Now in turn, you could model this GM stage by this small signal circuit model, and you can apply your Kirchhoff's current law that you're going to learn in, if you ever, I guarantee you're going to learn if you take Dr. E's circuits and device course. So you would do KCL and solve a differential equation that all you guys are going to know how to do once you, or you already know how to do. But what you'll see is that the input, the output to input has an exponential dependence on this C, on this load capacitance that's the result of all the comparators. Now, if you want to present an accurate signal for the comparators to compare, that sample signal has to settle, exponentially settle to a given value within a tolerable amount of error, which is defined by the ADC resolution. So if you want a high resolution data converter for N, then this error has to be 1 over 256. And it definitely has implications on the settling time. Because for higher N, you're going to get a higher C. And for faster operation, you want a small T settle. So what you're going to need to do is pump more GM or transconductance into the system, which translates to more current, which again translates to more power. So for higher accuracy and speed, you want more comparators for accuracy, but it requires more GM for speed, which translates to more power. If you do a I guess it wasn't simple. A similar analysis will show that you have the same relationships with the speed of the comparators. If you want to operate your data converter very fast, these comparators have to make a decision quickly, but you will see that there's also an exponential dependence between the input and the output, which depends on some capacitance and a GM stage. So to make a long story short, for higher accuracy and speed, you need fast comparators, but that requires more GM, which translates to more power. So what you're going to find is that for a high accuracy in your data converters, you want larger N. But for larger N, this capacitance is going to be proportional to, it's going to be exponentially dependent on that resolution N. So that translates into more power, and for a given, for a certain speed, if you want to go faster, you're going to have to pump more current into the system. So a nice problem, well not a nice problem, but a good problem to solve is to figure out a way of how to relax this speed, accuracy, and power trade-off that's inherent in this architecture. And I was fortunate enough to solve that problem at University of Michigan, which it's a top 4 public university and a top 6 engineering school, although it was top 5 when I applied. And has a gorgeous campus and a kick-ass football team that just adds to the whole college experience. So it has the highest R&D funding, which is great because basically it means there's a lot of funding to go around to do a lot of crazy stuff in the area of analog mixed-signal integrated circuits. Now the term mixed signal just means analog and digital. We apply analog and digital techniques in a wide range of applications. Now the term integrated circuits, all it is a circuit that's integrated on a silicon substrate, which is basically just a chip. It's your chip that performs a particular function. Now this research group was headed by my research advisor, who is a well-known and respected professor in his field, and who's the guy who gets to tell you when you graduate, if and when you do, right? So we do, this group does integrated circuits for many applications, such as brain prosthesis, wireless radios, fully integrated, fully integrated CMOS radios. So yes, we do radios, brain prosthesis, compressive sensing, and of course, a lot of different types of analog to digital converters. And so that's, for the most part, was the focus of my research. And so the whole process goes is that we try to come up with novel techniques that mitigates this problem of high power, this high power problem present in the flash ADC converter. So my first project was basically a 7-bit 1.5 gigahertz flash ADC. Now this architecture is similar to what I showed you guys, where you have an input switch, a bank of comparators, and an encoder that outputs a digital value. The novel techniques that we tried in this approach was simply to remove the reference value. We built the reference into the comparators, and we applied what we call a redundancy technique to increase the number of comparators that we use to build this data converter. So in a traditional 7-bit converter, you would have 128 comparators. But remember, they have to be accurate. So what we did is we traded off accuracy. Instead of large comparators, we built small, fast comparators, but we were able to use a lot more than 128. In fact, we used about 1,000. And we used digital signal processing techniques to build this data converter once you power up. And so this is what we call the layout of the chip of this data converter. It's essentially what it is. It's a blueprint. It's a visual representation of how the actual chip is going to look when you get it back from the manufacturing facility. So what you do is you go through the design process, and at the end you generate this blueprint that you send to the fabrication facility, and you get your chip and your prototype back, and you test it. Now, so one way of testing it is to apply a input signal to your data converter of a known frequency and of a known amplitude. And what you do is you use these test and measuring equipment to collect the ADC outputs. And from these ADC outputs, what you're going to do is just extract the frequency content of the ADC output and locate the signal that you actually put in the first place, and you compare it against all the other unwanted artifacts that are a result of the imperfections of your data converter. Now, to make the long story short, what you want is this signal here to be much higher than all the other noise, what we call noise and distortion terms. Now, not to get into too much detail, but this first pass of this data converter was, the performance was good enough to get it published in a respected journal. And the power was also pretty good. And so then you figure one chip, one prototype published, you need to go through the cycle a couple more times before you're set for graduation. So we came up with another technique that leverages what we call a two-stage pipeline data conversion technique. So what this basically does is just partitions the conversion into 2 steps. So for a 9-bit data converter, instead of doing the conversion in one cycle with 512 comparators, like I showed you what we would need in the flash architecture, you can do it with just the 4-bit in the first stage, where you would resolve it to 4 bits, and then you would resolve it again in the back end, where you resolve it to 6 bits. Now 4 bits plus 6 bits is equal to 10 bits, but we use that extra bit to do some correction. So this is another blueprint of the actual prototype. Blueprint of the chip, in which you send to the fab to get the prototype. Dimensions are 1 millimeter by 1 millimeter, and like I said previously, I believe the diameter of a penny is 20 millimeters. So it just gives you the idea of how small this chip is, and it's pretty crazy what it can do, because it just consists of a bunch of small little devices called transistors that you'll probably get into in Dr. E's circuits courses as well. Just not at deep level, but I remember being exposed to that. Once again, the overall what we call the power spectrum showed good performance, and we were able to we published this at a conference called the Asian Solid State Circuits Conference, which was held in Japan that year, which was pretty cool because you get to fly to Japan and network with other students and professors and folks that work in the industry, and make connections, basically networking. But at the end, it was also pretty cool to party it up in Tokyo for 4 days after. So one thing about this particular chip is that this plot alone, this finally kind of defined my, okay, you're ready to graduate, which is kind of, it's kind of not having seen this before. This basically equals a Ph.D., which is, what is it? It's just a weird plot, right? But for old time's sakes, we did one more project where we did a 9-bit 2 gigasample per second. Basically, it operates at 2 billion 2 billion cycles per second. But what we did is we took the second chip and we time interleaved it. Essentially, we ran two in parallel and alternated the conversion process, and we stitched the ADC outputs together. Once again, we went through the whole generate the blueprint, ship it to the fabrication facility, fab for short, and we tested it in the lab, and the performance was pretty good. And we were able to publish this at a European Solid State Circuits conference, which was held in Romania that year. So I got to travel to Europe for the first time. And so we get through the whole Ph.D. process where you start off in your cubicle, where you design your circuit, you simulate your circuit using computer automated design tools that for the most part gives you, it simulates how the actual circuit is going to behave in real life. You use and you continue to use these CAD tools, as we call them, to generate the blueprint, and then you get the tape out. Tape out basically means is you ship your blueprint to the fabrication facility, the manufacturer. And so the time between tape out and by the time between you get your chip back, what you're going to do is you're going to design your test board, your PCB test board. So you're going to design and assemble your test board is going to allow you to plug in your chip. It's going to allow you to talk to your chip with a computer, and it allows you to measure the performance of the chip. So once you get the chip back, you plug it in, and if you're lucky, it works. If you're unlucky, if you did a silly mistake, you're back to the drawing board. I was fortunate enough to, pay enough attention to the details to have 3 chips and 3 functional chips in and out, which resulted in 3 publications, which is the third step in this whole process. So you get to publish your paper, you have to write your paper, and depending on the deadline for a conference, you're going to be testing and writing at the same time, so that when you have the data, you're going to just plug in the numbers and submit it for acceptance. Now this alone could take a while as well, because you have to debug your chip, you have to write your scripts, your programming scripts that's gonna allow you to talk to your chip using a computer. It's gonna allow you to talk to these test and measurement equipment to apply signals to your chip. So after 3 rounds, then the last step is to write and defend your thesis in front of a committee but basically a committee is your other professors that are going to decide whether or not your work is for the most part, is it good enough for a Ph.D. So you defend your thesis in front of a committee and your peers, and then you sleep for days, because it really takes a lot out of you. And I gotta say, this is probably so far the most challenging and rewarding part of my life at the moment. But it also it prepares you for basically it prepares you for industry. So with this experience, I was able to hit the ground running and be involved in a project that is going to have an immediate impact on the continued success of the company, as well as getting it published in a well-known and respected conference. So off the bat, out of Michigan, where my last chip was a 2 gigasample per second ADC, I started working on a 28 gigasample per second ADC, which is 28 billion cycles per second. So those pictures that I showed you of the data transmission, that's being transmitted and received by this ADC at a 28 gigahertz, which is every 35 picoseconds. And once again, a picosecond is 1 second divided by a trillion. And we got some pretty good press here. What else do I want to say? Okay, that was pretty quick. So I guess at this point you probably thought that, okay, this guy had his head on straight and he knew what he wanted off the bat, but that was far from the case. So I guess we could take, Aaron wanted me to tell you a little bit of my story, so we could turn back the clock and go to back to senior year in high school. What you're going to find is I had a 2-point question mark GPA with a focus in football and soccer, and I was taking 2 lunch breaks, and what was the occasional ditch day became the frequent ditch day. And seriously, we had the attendance office secretary would go to class and pick up my best buddy and me and walk us to our next class to make sure we didn't skip out and take the first round of lunch. So anyways, regardless of all this, my mom, she wanted me to go to college, and she's going to make sure I go to college regardless of what I say, right? She would have dragged me by the ear to JC if she could. Well, I'm sure she could. So it didn't sound like a bad idea at the time, because it's either go to school, continue school, or get a job. And getting a job, perished the thought at that time, right? So nevertheless, I ended up applying to college in San Mateo, but with the goal of playing football. So in that process, you had to take some entrance exams to size you up of what courses you're qualified, or I guess you'll be able to take. And so my English wasn't so good. Go figure. Growing up in the U.S., I still had a terrible grammar apparently, and I had to take what they called bonehead English. And they call it bonehead English because it doesn't even count for college credit. I don't know. I'm sure they still have that, but I'm not sure if they still call it that here. And I also took a class called College and Career Awareness because I didn't really know what I wanted to pursue in terms of a major, and I figured this would help me out. And on top of that, I did take applied calculus because even though I was, for the most part, a slacker in high school, I did continue taking the math classes, even though I already had met the requirement for graduation. I just didn't do well in them. Never really applied myself. So that was my first semester, and one of my football coaches, Coach Heron, I gotta look him up. He noticed that I was the only guy on the team who was actually taking a calculus class, and so he encouraged me to look into engineering. He encouraged me to look into engineering, and one way of doing that for 18-year-olds is just to tell them how much money you're gonna make once you get that degree, right? But anyhow, so I took his advice, and so I went over to my counselor, Sylvia Aguirre, at the, I guess it's the extended, she works at the extended opportunity offices at CSM. She's still there to this day. So I went to her office, and she sat me down, and we went through a plan of all the classes that I needed to take to get to be able to transfer to where I wanted to go, was UC Berkeley. I figured if I'm going to do this, I'm going to shoot for the top, right? But which is not bad, because even if you don't get in, probably everything that you take here is transferable to all the other UCs, as well as some good state schools. So after I finally decided to, okay, let's go for this. I spent the next 2 years. So the first year was, the first year I took courses that actually wasn't going to help me get into the engineering program. But once I found my direction, I spent the next 2 years taking all the calculus courses, the linear algebra, the differential equations, the physics, and so forth. So that is required to transfer to the UC. On top of that, I took courses that didn't even count for UC, but it looks good on your transcript. And so I spent the next 2 years going between CSM, Kenyatta, and Skyline College. And there were instances that I would start off with an 8 a.m. Physics lab at CSM, went for 3 hours, and then I would have a 1 p.m., I believe it was either material science or circuits and devices that Dr. E was teaching. And that lasted another 3 hours. Went back to CSM, did a little bit of homework in the library, just enough time until my 7 p.m. Assembly language course. In the same cycle, I guess the next semester was for the most part the same deal, but this time it was for Calculus 3. And I told one of the students here that it's no fun taking Calculus 3 at 7 p.m. from 7 to 10. I mean, that's the last thing you want to do, but I had to take the courses that for the most part is gonna get me to transfer as quickly, because I had already spent 1 year, and and I didn't want to spend another 3 years, so it was pretty impacted. But I wanted it. I wanted to get in Berkeley so bad that it just all I could think of was getting those straight A's, getting those straight A's, getting those straight A's. I just remember taking the circuits and device courses with Dr. E, and the first exam I ended up getting an 86% because I screwed up some current loop equation, and I wasn't having that. And I was like, oh, you know, he was letting students take retakes who didn't do so well, and I was like, Dr. E, you gotta let me take that exam again. And he's like, you don't need to. It's like, no, but I want to take it. And he's like, okay, but if you do worse, you know, this is going to count against you. But I ended up getting a 98% again, and so that bumped me up to above 90, and that's what I wanted. And so it was like that for the next 2 years in every single course, because that's what I wanted to. That was my goal, was to transfer to a top engineering school. And so my last semester, my counselor, Sylvia Giddes, she recommended that I apply to this program called Inroads. I don't know if you folks have heard of it, but I definitely encourage you to look this up because once you're ready to transfer, you'll be eligible to apply to this program. And what it is just, it's a mission of this, the mission of Inroads is to develop and place talented, underserved youth in business and industry and prepare them for corporate and community leadership. So you go on retreats and you're taking some courses, seminars basically, that teach you things from how to manage your finances and how to manage your time, and other seminars that companies pay a lot of money to send their employees. And we had, and us students who had the opportunity to be a part of Inroads were getting that for free. On top of that, they place you in industry with an internship that kind of aligns with what your interests are in school. And so through them, I was able to get an internship at Hewlett Packard. My last, when was this? Yeah, so right the summer before I transferred to Berkeley, I already had a internship, which was pretty cool. But it was at Hewlett Packard where I actually became interested in data converters. So now hopefully you'll see how it all ties in. And from my internships at HP, which ended up being three summers, like I said, that's where I became more interested at the hardware level. Because when I was in Berkeley, I was trying to decide whether or not I wanted to do software instead of hardware. Now I kind of wish I did software because software is a lot harder than it's hot now as opposed to hardware. But you shouldn't. You got to do with what you got to do what you like, right? What you're passionate about. So I guess that ends it, and Aaron asked me to, I guess, give you some advice. What I recommend you guys do is, I guess, just to get, all this stuff you've heard it before, but I guess there's a reason for it because it's true, right? Just be motivated. Find your motivation. My motivation is I just wanted to make my parents proud. I mean, my mom, she was just had a 6th grade education. She came to this country and cleaned houses for her whole life, and I just wanted to make her proud. And also, you wanted to, almost straight up there. Also, to stay focused and work hard. I mean, you gotta want it. If you want to be one of the best, you gotta work hard at it. I mean, example, retaking these exams to get an A, and now that I think about it, that's not the only thing, right? But my mindset at that time, it was just, maybe I was too focused. But anyhow, work hard and also take advantage of the resources available. Definitely get involved. Definitely take advantage of the professor's office hours. And I'm being dead serious on this. Just even if you don't have any questions, it's good to listen. Good to listen and hear what other students are having trouble with, and it just starts to click. At the same time, get involved in your school and your community, because not only because it's good, but beneficial, but to the community, but also your 4-year schools like to see that. One more thing, I guess I want to mention study groups. Go to the library, work in groups, because even if you know the courses, even if you know the material, it's good to explain it, and because it just gives you more insight. And if you were anything like me, I recommend you stay out of trouble, because it's just one mistake could pretty much end it. And at the end, just go for yours. Basically what I mean is that nobody's going to give you anything. folks, they'll open doors for you, but you're the one who has to walk through it. And so I urge you to take this advice and then just go do it. I wish you all the luck. And I guess that's it. Hopefully I didn't speak too fast, but I'll answer any questions. Yes, sir.
Pardon my asking, but do you happen to know where you and your company see themselves in about 10 years' time?
10 years' time, hopefully we'd get bought out and then I'll cash in on my stocks. Okay, so basically we are in the datacom market, and we just had actually it's a coincidence that we just did a deal with Microsoft to redefine the way data centers are structured. So 10 years from now, we'll either be a powerhouse like, say, companies like Qualcomm, or we'll get bought out by a company like Qualcomm or Intel. So either way, I think the technology that we're developing is going to pioneer, it's going to stay here for a while.
And for the manufacturing of the chips, how do they do it exactly? Like, how do they develop the different micro devices and such on it?
Yeah, so let's see. So basically the blueprint is just a bunch of rectangles and squares that you place together that defines the metals and the routing and the actual transistors themselves. So they put this blueprint under, I guess you could say, a lens, and they use a technique called photolithography to etch the shapes into the silicon substrate. And it uses a material that's we call a semiconductor because it conducts it conducts current as well as it insulates from current. And so you could use these transistors as a switch that turns on and off, and you put these transistors together to build anything from like I showed a data converter. So this process is really expensive, and the more technology progresses, the smaller and smaller these devices are getting. And not all the companies can afford to have their own manufacturing facilities, which is why we use the term fabless semiconductor company, meaning that you outsource it to these huge manufacturing companies that have the R&D, that have enough revenue coming in to invest in this manufacturing techniques. Yeah. Any more? Going once, going twice? Yes, sir.
So for your analog to digital converters, does your company ever like dabble with trying to find ways of having old technology connect to current technology? In terms of Google was talking about maybe perhaps 50 or 60 years from now there might be like a good 30 or 40 year period of data that's just not accessible anymore because no one's bothered to try to convert the old analog information into digital.
So, yeah, there's many efforts even by Google to kind of document everything and transfer it digitally. In terms of accessing old data, these systems that get built have to have what they call backward compatibility, I guess, right? But moving forward, everything is going to be in the digital domain. It's going to be in the cloud, so to speak.
Yeah.
So, I don't think I answered your question.
This one isn't quite as serious. Did you ever sort of compare the work you do with others such, well, not quite.
Another, excuse me?
Well, did you ever compare the work you do with what we imagine already? Do you see yourself bringing electronic dreams to reality?
I'm not quite getting the question.
Do you think you're doing well or not?
There you go. So this data transmission technology, this PAM4, is the next. This is where the industry is going to ship your data as fast as possible, and you're going to need more and more. The best way of doing that is to use a data converter. So as of now, the market is hot for high-speed, moderate resolution, meaning not high resolution, not low resolution, data converters. So these architectures, there's a lot of research going into how to make these guys faster but lower power, because power is everything, right? So it's a good time right now to actually be in this area. And it definitely, at least I feel it does have an impact, because it facilitates the way people communicate. Right? Like I said, I can post 2 selfies on Facebook now at the same time. So the bottleneck is in the, definitely in there's some bottlenecks in the data converter, but it's more in the channel. You send the data out across a fiber optic wire or a copper wire, but when you receive the data, it's noisy. It has a lot of imperfections. So you need a data converter to convert it into the digital domain, so a digital signal processor can clean it up and ship it back out. So the bottleneck is, like I said, is the channel and the power required the power requirements to ship the data out at very high speeds, but be able to reliably receive it, clean it up, and send it to a data center, a server, computer. So I think the bottleneck is power, because you could either send the data out in a bunch of parallel channels or send it out in a single channel. But the parallel approach, just like the single channel approach, there's power implications. Power is the main bottleneck, because especially since these modules have to fit on a board and they have a limit to how much heat it can take. These things get pretty high in temperature, and how much power. Yeah, it comes down to power.
Thank you very much. I think you're going to stay around and answer my
Stick
questions.
around for any more questions.
And I think Dr. A also wanted to say happy, so. And one quick announcement, there's still room for the San Jose field trip this Friday, so I have forms here. If you're interested, just grab one, and there's still room. There's pizza, so you guys could grab another slice of pizza or cookies, and don't forget your cards. Thank you. Thank you again.